Yes. Talks are to really connect the world and the universe through science. Science has no national boundaries, and we really want to bring the world together through science and then the scientists and promoting science and scientists. So my name is Jagadish. I am the professor of physics at the Australian National University, and I'll be serving this evening as the moderator. So we've been really featuring some of the top scientists in the world in the iCANX talks in the March. We have had Professor Bob Langer from MIT and Professor Martin Green from University of New South Wales. And then today we have got Professor Yasuhiko Arakawa from University of Tokyo. And the next week we are going to have Professor Naomi Hallas from Rice University. She's going to talk about the plasmonics or so. So really, so we also have got challenges, and then typically what we do is that we encourage the young people to bring young people on board and then act like challenges during the panel discussion after the presentation of the main speaker, Professor Arakawa, today. And these are the four the challenges, those are participating. And today's challenger is Changhao Lee from MIT. He is a PhD student there, and I'll come back and talk about him. So the today's speaker is my very good friend and a very distinguished colleague, Professor Yasuhiko Arakawa from University of Tokyo. Professor Arakawa doesn't need any introduction because he's world-renowned in the field of quantum dots and optoelectronics. And Professor Arakawa did his PhD in 1980 from University of Tokyo, and then the same year he has been appointed as an assistant professor. In 1981, he has been promoted as an associate professor. And in 1993, he has been promoted as a full professor. And then currently he's serving as a special professor. And then also he's serving as a director of their quantum activities. And then most of his career he spent at University of Tokyo, except for a couple of years at Caltech. And as he visited Caltech and then worked with Professor Amnandiari, and then done some pioneering work while he was at Caltech as well. So he's really won many awards and recognitions, and I can spend half the talk time just telling about all his awards. Some of the prestigious awards are the IEEE Nishizawa Medal, IEEE William Stryper Award, and then Heinrich Welker Award, and the Prime Minister's Prize from Japan, and then also the Leo Isaki Prize, and many, many awards he has won. And so he is really world-renowned in the field of quantum dots and truly identified as a pioneer in the field of quantum dots. We're delighted to have him today as part of the iCANX talks, and then he's going to talk about quantum dots from science to applications. Professor Arakawa, please.
Okay, thank you very much, Professor Jagadish, for your kind introductions. First, let me start my file. Okay, can you see that?
Yep.
Okay, just a moment. Okay, so my name is Yasuhiko Arakawa from the University of Tokyo. So it is my great honor to give a presentation at the iCANX talks. I would like to again thank Professor Jagadish and Professor Zhang, also Professor Wang, for giving me an opportunity to give presentation here. So let me begin with this TM photograph. This is a epitaxial ground quantum dot with the size of about 10 nanometers. In this small structure, we can confine two electrons with different spin populations. Sorry, the same, with this spin different positions at the same quantized energy levels. For investing in this structure, we have to consider that full quantization, spin effect, and electron correlation are main physics. In addition to this, we have to consider or take account of the photon electron interaction, that is light matter interaction, that are essential for photonic devices. Moreover, we have to consider the photon electron interactions as well. Our goal is to realize control of photon electron interactions and photon electron interactions by using quantum dots together with photonic and phononic nanostructures such as photonic crystals. But today, time is limited, so we focus on just a part of these topics. This is the outline of my talk. After a brief introduction, I overview quantum dot research. Then I will discuss application to silicon photonics. Then I will discuss a single photon sources, and finally I will summarize my talk. Okay, this year, last year of 2020, the 60th anniversary of the lasers. Due to COVID-19, many events celebrating this anniversary have been postponed to this year. The laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic field. The term laser originated from is an acronym for light amplification by stimulated emission of radiation, as all of you know. The first laser was built in 1960s by Theodore Mayman at the Hughes Research Laboratories, based on the theoretical work by Charles Towns and Arthur Charles. Regarding semiconductor lasers, in 1962, gallium arsenide homogeneous laser was demonstrated at low temperatures. And in 1970, room temperature operation was realized by using double heterostructures. Ivan Alferov and at Yale Institute and Izuo Hayashi and Casey Panish at Bell Laboratories are mainly contributing to this realization of the room temperatures. So here, the gallium double heterostructure plays very important roles because both carriers and the electromagnetic field or optical field are confined by using this double heterostructures, because both refractive index and energy band gap can be smaller. Energy gap is smaller and the refractive index is larger in this double heterostructure. Okay, so usually in the bulk materials, bulk semiconductor, the electron, the holes are freely moving. So in double heterostructure lasers, also the same situation occurring. If we have the small structures, the station is changed. Electrons are confined three-dimensionally. And so quantum dot can be realized. So when I started to work on the quantum size effect, if we confine completely the carriers inside such small structure, what happens? This is the first question that came to me. This simple question in my mind came to the idea of the quantum box in which electrons and holes are confined three-dimensionally. If the size of the quantum that is similar to the double wavelength, that is actually 10 nanometers, electrons are fully quantized and the wave function nature is pronounced. Also, this box is similar to electrons confined by Coulomb potentials corresponding to atoms. Therefore, sometimes the quantum dot is called artificial atoms. My idea was also based on superlattices and quantum wells. In 1970, Leo Esaki and Tsui proposed a superlattice structure at IBM for resonant tunneling diode. If the barrier layer becomes thick, electrons are isolated each other and the freedom of electron motion becomes 2. This is called quantum wells. Nowadays, quantum wells are key nanostructures for many practical devices, such as quantum well lasers, quantum cascade lasers, high electron mobility transistors, quantum well infrared detectors, and quantum confined stark effect modulators in the real world. My idea came to me being inspired by Leo Esaki's superlattice and quantum wells. In 1982, I proposed the concept of quantum dots and its application to semiconductor lasers. We predicted to reduce temperature dependence of the threshold current. This calculation based on the simple models shows that the temperature dependence of the threshold current is fully suppressed in the quantum dot lasers as long as carrier population at the higher subband can be ignored. Furthermore, by placing semiconductor lasers in a high magnetic field, the reduced temperature dependence was successfully demonstrated. Let me discuss in more details. This is a gain expression of semiconductor lasers in this formula. Dipole moment, Filip interact function, density of state are included. When quantum dots are p-doped, this expression becomes more simplified like this. So finally, gain is proportional to the product of the Fermi-Dirac function and the density of state. When junction temperature is increased, the Fermi-Dirac function is broadened with the order of kT. On the other hand, the density of state depends on the freedom of electron motion. With the decrease of the dimensionality, the broadening of the function density of state can be suppressed. As a result, the gain function is more suppressed. The broadening of the gain function is more suppressed with the decrease of the dimensionality, even if temperature is increased. In the case of the quantum dot lasers, the density of state is delta function-like, and even if a Fermi-Dirac function is changed with the increase of temperature, the gain profile does not exchange, which results in temperature insensitivity, in temperature insensitive threshold current. Of course, this discussion is based on existence of higher excited state, or based on the assumption that we can ignore the existence of the higher excited state. Here, I just would like to notify you that there has been some claims that quantum dot was proposed in the Dingle's patent filed in 1976. Dr. Dingle, as you know, was a Bell Laboratory researcher who invented modulation doped transistors in the mid-1970s, and he did other big research as well. In his patent, 3D, 2D, 1D electrons were discussed. However, there was no concept, no description on the concept of the quantum dot that realized zero-dimensional electrons in the patent. Anyway, when I proposed the concept of the quantum dot lasers, it was impossible to realize the quantum dot structures. At that time, even high-quality quantum well was not easy to be grown. And therefore, I theoretically worked on the quantum dot lasers, including enhanced differential gain and reduced alpha parameters, so on. For experimental simulations, we placed quantum well lasers in a high magnitude field, with which one-dimensional confinement by quantum well potential and two-dimensional confinement by the Lorentz force are realized. Thus, we succeeded in demonstrating the quantum confinement effect in the semiconductor laser. This kind of experiment was done in Tokyo and also in California with Professor Bahara and Professor Yarif by visiting MIT National Magnet Laboratories sometimes, while I was Caltech for 2 years, from 1984 to 1986. At the time, Professor Bahara was a graduate student. I thought the quantum laser I thought the quantum laser could not be realized before the end of the 20th. Maybe would not have been realized before the end of the 20th century. However, progress is much faster than my forecasting. In 1985, Connect group in France discovered the transit cluster growth mode accidentally when they tried to grow indium arsenide, gallium arsenide strained superlattice structures by molecular beam epitaxies. And they observed a defect-like island. They are very smart, and they found that the islands are coherent structures exhibiting a bright luminescence. Since then, many groups started to work on this self-assembled quantum dot structures. The main mechanism for formation of self-assembling quantum dot is lattice mismatching between gallium arsenide and indium arsenide, which is led to the accumulation of the surface energy, strain surface energy. There are 3 modes for the deposition of the lattice mismatched materials on substrate. One of them is the transit cluster growth mode that causes reconfiguration of surface atoms, resulting in the coherent island with wetting layers. After connecting the group report, many groups started to grow started to try to grow this 3-dimensional structures by the transit cluster growth mode. At the University of Tokyo and in collaboration with Fujitsu, we also started to work on the formation of the quantum dot structures, focusing on 1.3 micron. And in 1995, we found, exactly speaking, Fujitsu found that quantum dot formations emitting at 1.3 micron. Higher density than multi-layer was realized like this. And also, in addition to isolated quantum dot structures, shape control by stacking can be realized like this. And particularly, this is important for quantum dot amplifier application and the polarization independent insensitivity quantum dot can be realized. And the wavelength controls was also investigated. And we made the effort to increase the density of the quantum dot for realizing higher gains. This is just to illustrate how to fabricate the quantum dot lasers. We grow quantum dot structures. Each layer has a high density quantum dot, and we stack the quantum dot by the molecular beam axis. And then we have finally process the wafers, and we get the quantum dot laser chips. Since then, many groups have started to work on this self quantum dots. As I said before, the first trial to realize quantum dot laser was reported in 1994 by Technical University of Berlin and the Yole Institute. You can see the names of Professor Weinberg and Professor Alfer here. You can see the characteristics, and so still, of course, this is a preliminary result, but it is also one of the important milestones for the progress in the quantum dot laser. Regarding the 1.3 micron quantum dot lasers, Fujitsu laboratory, as I mentioned before, developed 1.3 micron self-assembled quantum dot structures. And University of Texas realized pulsed operation at room temperature. Finally, CW operation was realized by Fujitsu laboratory. And you can see the luminescence, the blazing spectrum from the semiconductor laser, quantum dot laser chips. And below the threshold, you can find the luminescence corresponding to ground state and the first excited state and the second excited state. This evidences that discrete energy levels are realized inside the quantum dot lasers. Okay, this is a trend of the threshold current density for bulk lasers and quantum lasers and quantum dot lasers. This abrupt reduction of the threshold current is the invention of the double heterostructures. And the quantum laser also realized a reduction of threshold current. And currently, the lowest threshold current is realized by the quantum dot lasers. When I proposed the concept of the quantum dot lasers in 1982, together with the quantum dot lasers, of course, one-dimensional quantum wire laser was also discussed. And so therefore, the progress is, would be maybe made step by step from bulk to quantum wells, and then this would be quantum wires. However, they occurred jump or skip, and the quantum dot laser is has been realized actually. So therefore, I don't think quantum wire laser will not be maybe appearing even in the future. Okay. Of course, the low threshold current is very attractive. However, if the quantum dot laser has just this characteristics, it is not so easy to compete with conventional quantum lasers with smaller cavities and so on. So we should find out the unique features of the quantum dot lasers. As predicted in 1982, one of them is high temperature stability. Indeed, finally, in 2004, University of Tokyo and Fujitsu succeeded in realizing high temperature stability of the quantum dot lasers by growing high quality quantum dot structures. In addition, high temperature stability can be led to high temperature operations. Indeed, the quantum dot lasers can be operated to 220 degrees Celsius. This operation temperature is still the highest operation temperature among any kind of laser in the world. So at that time, we also demonstrated the temperature insensitive 10 GBps modulation. So we realized using high-speed operations in the temperature ranges from 20 degrees Celsius to 90 degrees Celsius. This expression is resonant modulation frequencies. That is almost corresponding to the modulation speed. And here, the gain plays very important roles. Exactly speaking, differential gain is placed here. The gain is inversely proportional to inhomogeneous broadening or the size variation, and proportional to the number area density of the quantum dots, and also the number of quantum dot layers. So therefore, from the point of the high quality quantum dots, from the point of growth of the high quality quantum dots suitable for lasers, we should make effort to improve these parameters. Indeed, we succeeded in realizing succeeded in improving dot density, area density, influence broadening, and also modal gain. And you can see the clear difference between the two FM images. And finally, bitrate can be increased up to 25 Gbps modulation at that time. Based on these achievements, in Japan, in 2006, QD Laser Incorporation was launched as a spin-off company of Fujitsu companies. The unique features: temperature stability, high temperature operations, and 1.3 micron wavelength on gallium substrate are important for the companies. Indeed, the company found various markets, not only for telecom, but also high temperature operations. The market which want to need high temperature operations, and also high power operations, and also silicon photonics. So now, more than 1 million chips actually annually delivered to commercial market for telecom applications. And also, just recently, they achieved the IPO. Yeah, just 1 month ago. Regarding high temperature operations, as I mentioned before, the quantum dot laser can realize the operation temperature up to 220 degrees Celsius. Such a high temperature semiconductor lasers are needed for the data transmission, optical sensing, and so on in variety of the large things. And also automobile, desert, plant, and underground explorations, and so on, a very important market. For this market, the price of each chip, one chip is much higher than those in the telecom market. Another important target for the quantum laser is the silicon photonics. Here, I would like to explain briefly why the quantum dot laser is important. As all of you know, silicon photonics is very important for saving power consumption, solving material interconnects, bottlenecks, and providing a promising platform for large-scale quantum dot photonics, quantum photonics technologies in the future. So therefore, lots of attention is received, and also many good companies and the universities are making effort for silicon photonics. And modulators and the detectors and so on, most can be realized by silicon processing. So, but however, there is a limit of silicon, as you know, that is the light sources. To realize the silicon light sources, silicon gamma lasers, gamma lasers have been investigated. However, still we need to have the 3-5 lasers because in silicon we cannot avoid or we cannot solve the problem of indirect band recombination process. So still we have to utilize direct recombination and using 3-5 lasers. So therefore, hybrid integration of the light sources on silicon system is very important. Particularly the quantum silicon hybrid light sources is the best solution because of the low threshold current, high temperature operation, high tolerance to optical feedback noises due to the small alpha parameters, and also for quantum photonics technologies, this quantum dot structure can be applied to single photon sources on silicon. So here I'd like to briefly discuss the silicon photonics technologies. There are 4 methods, 4 techniques to integrate quantum dot lasers on silicon: rich bonding, direct epitaxial growth, and wafer bonding and transfer plating. Here I will describe these 3 methods. Okay, so first I will discuss rich bonding, and we have the Filip implement laser chips onto the silicon circuit, and this is the space of the silicon quantum dot laser arrays. And of course, alignment is very not easy, but they established this technology. This is a 5 millimeter square silicon photonics chip, and including modulators and detectors. So finally, in Japan, national project and realized very 5 millimeter square, very small chips include for the transceivers with a quantum dot laser. 5 milliwatt gigabps, 5 milliwatt per gigabps, 25 Gbps per channel, and so on. And high temperature operation was realized. It is very important because sometimes these chips will be placed near the LSI chips, and no optical isolator is needed, thanks to the small alpha parameters. Indeed, we have achieved high temperature operations in other transceivers without any isolator. Okay, this is the first method of the quantum dot lasers onto silicon. The second is the direct epitaxial growth. So even 30 years ago, many people tried to 3-5 semiconductors on silicon substrate. However, there are many problems: mismatched polarities, mismatched lattice constant, mismatched thermal expansion coefficient. So anti-domain, phase domain effect, and threading dislocation cannot be avoided. At that time, 30 years ago, they tried to grow 3-5 semiconductor lasers using quantum lasers, the bulk lasers. In this case, threading dislocation causes the degradation of the non-intermediate plays a non-intermediate combination, causes non-intermediate combinations because carriers are moving freely. So therefore, finally, this is captured by the threading dislocation. However, in the case of quantum dot structure, once electron-hole pairs are relaxed inside quantum dot structure, this is free from the threading dislocation. So therefore, the quality of the quantum dot laser should be much better than that of the quantum wave laser. Indeed, many groups, including USB and the University College of London or Hong Kong University, have been investigating this direction and using patterned silicon substrate or as a template grown by MOCVD and so on. So here we investigate the direct epitaxial growth of quantum dot lasers on axis silicon 100 by all MBE. So here anti-domain phase domain effect can be avoided or suppressed by using by growing buffer layers on silicon very carefully. And also threading dislocation can be suppressed by using strained layer superlattices, dislocation filter, and so on. So finally, we succeeded in the first direct epitaxial grown quantum dot lasers on axis silicon 100 substrate by all MB. We don't need to use patterned substrate or template grown by template by the grown by MOCVD and so on. Okay, so finally, I briefly mentioned transfer printing method. This is a technique based on simply pick up and place assembled by the stamp, like a stamp. This enables the precise position control of the large target elements. And this is the process, stamp, pick up, and above, and also position, and the final print, and so on. Indeed, we try to place nanobeam quantum lasers on the SOI silicon waveguide. And here, there's a gap defined by silicon dioxide. There should be some optimum gap between the for realizing high quality factors and high efficiency coupling. If the gap is smaller, coupling efficiency can be improved. However, cavity quality factor is reduced, and so on. So therefore, there should be optimum. The optimum gap is around 0.6 micron and so on. Then we fabricated gallium arsenide nanobeam cavities, and this is pattern formed on the wafers, and this was picked up by PDM's rubber stamps. And in parallel, we prepared the CMOS silicon structure. This was fabricated by the foundries, and And then the laser structures is transferred and transfer printed on the silicon substrate. Sorry, silicon waveguide. So indeed, this is the nanobeam structure, laser, nano lasers, and this is silicon waveguide. And these are grating output couplers. And if we place one laser here, we can see lasing oscillation from the output couplers. And this is ideal characteristics. And after that, we can also place another laser by using a transfer printing. Then we have the lasing oscillation again with different lasing wavelengths. This is spectrum is measured from the above the samples, and this is measured through the waveguide and also output couplers, so on. Okay, this is a roadmap by the Yole development made in 2018. Here for silicon photonics roadmap, and so you can see waveguide and photodetector and so on. And they discuss also laser light sources, and they put quantum dot lasers here. But already in 2019, by using Fritz bonding, silicon photonics is a chip with a quantum dot laser became commercially available from one company just started in 2017 for the IO other 5 millimeters transceiver, other 5 millimeter square transceivers. And in the future, wafer bonding and the direct texture growth will be realized. In the wafer bonding or transfer printing method will be realized in 1 or 2 years, and finally direct texture growth will be maybe realistic growth, implementing hybrid laser realization technique. Okay, so far I have been discussing so-called conventional type quantum lasers. In our laboratory, in addition to these conventional quantum lasers, we have been working on quantum dot nano lasers and quantum dot nano cavity effect and so on. Single quantum dot lasers, 3D photonic crystal quantum dot lasers, and also we discussed the cavity QED effect with quantum dot structures, and the nanowires, quantum dot lasers with plasma-like effect, and 1D topological lasers, so on. And also single photon sources are very important targets for us. And this includes single photon sources up to 1.5 microns, and also high temperature operations at room temperature and 350 Kelvin. So here I will focus on this part using the remaining part of my talk. Okay, so this is a single photon, in some sense, single principle of single photon sources. Already, even in the beginning of 2000, several lasers have been investigated at shorter wavelengths. And also the operation temperature was, of course, low temperatures. So principle is very simple. You can have just one electron pair is populated inside the quantum dot, and a single photon can be emitted. There was challenging issues. There were challenging issues, and the telecom wavelengths, and the position controls, and high temperature operations. regarding position control, as you know, the quantum dots are randomly distributed. So therefore, it is not so easy to control the positions. So regarding the telecom wavelengths, already maybe almost 15 years ago, indium gallium arsenide indium phosphide quantum dots was realized for single photon sources. And we demonstrated single photon emission at that time. And position control can be solved by using selective area growth, and high temperature operations can be solved by the gallium nitride quantum dot structures. So here we focus on the topic on the high temperature operation together with position control. So let me briefly discuss the principle of the single photon emission. And this is one electron hole. This is the band diagram, and one electron hole pair is generated, and the exciton is realized. And if due to the spin effect, we can have two electron hole pairs inside a single quantum dot structure. If the energy of these two transitions is the same, we cannot avoid that two photon emissions. However, due to the bi-exciton binding energy through the correlation effect of the electron hole pairs, we can see the slightly different emission energy between the photons from the bi-exciton to exciton and exciton to ground state. So therefore, if we have the optical filters, we can guarantee that the single photon emission can be realized. However, with the increase of the temperatures, this spectrum is similar to this region. So therefore, we cannot avoid also emission of the two photons. Typically, indium arsenide quantum dots, the bi-exciton binding energy of indium arsenide quantum dots is just a few millielectron volt. That is much smaller than KT atomic temperature, 27 millielectron volt. So therefore, we cannot avoid such kind of contamination of the bi-exciton transitions. So we have to find out other semiconductors which can realize large binding energy of exciton, bi-exciton. So 3 nitride semiconductor is a good candidate because this has a large effective mass and also large exciton binding energy, so on. So we try to use gallium nitride based quantum dot structures by growing by ourselves high quality gallium nitride quantum dot structures. Indeed, already 15 years ago, we have very high quality quantum dot gallium nitride quantum dot structures on aluminum nitride. And we observed spectrum and bi-exciton and the exciton and the 32 millielectron volt difference can be seen. And because this is corresponding to the bi-exciton binding energies. And interesting thing that this bi-exciton peak is located at the higher energy side of the exciton. So therefore, we should say that a negative binding binding energy, not meeting binding energy of exciton. So bi-exciton, there are so many mistakes, is realized. And this can be explained by the built-in electric field due to the spontaneous emission, polarization and the piezoelectric polarization. In this case, we cannot avoid the built-in electric field inherently formed in the heterostructure. So therefore, electrons, the quantum confined Stark effect cannot is existing, and the electrons are pushed to this side, and the holes are pushed to this side. Even if two electron hole pairs or the biexton is generated. So therefore, repulsive force is more dominant than that of the attractive force. As a result, we see the negative binding energy. But it's okay because absolute value is the most important. It should be larger than 23 milli-electron volt. And we try to the autocorrelation measurement for checking the whether we have the single photon emission from the quantum dot structure. This is an experimental result, and if in the ideal case, at the delay time of 0, we should see the value which is called G to 0 should be equal to 0. However, and if this is smaller than 0.5, it's okay. And at 200 Kelvin, we succeed in observing G to 0 below the 0.5. So therefore, we were very happy to realize the highest temperature at the time for the single photon emitters based on the semiconductor quantum dot structures. However, this was done in 2006, and however, we could not realize higher temperature over 200 Kelvin. This is mainly due to probably some kind of dislocation effect because nearly existing quantum dot structure. So therefore, we decided to change our method, and we try to combine nanowires and the quantum dot structure. Because nanowire is investigated by Professor Jagadish very intensively, and we are also following his result. And we try to form two types of devices. One is, of course, single photon emitters or single photon sources. The other is nanowire quantum dot lasers. And today, I will discuss just single photon emitters application. So advantage of the nanowire quantum dot for single photon source is the following. We can suppress dislocation, the propagation, because dislocation can be terminated around here. And also high light extraction efficiency can be realized. And the cytocontrollability by selective area growth technique can be realized. And indeed, we have the very nice gallium nitride-based quantum dot, nanowire structures. And on the top of the structures, we form quantum dot structures. The actual size, lateral size is 10 nanometers, and the thickness is around 1 nanometer or something like that. If we compare the two kinds of dot, nanowire quantum dot and the scale quantum dot, we see the clear difference. Height is different, and the height is much smaller than in the nanowire quantum dot structures. And this can be led to suppression of the quantum confined Stark effect. So therefore, oscillator strength can be much increased compared to scale quantum dot structures. We investigated the spectrum, single dot spectroscopy, and we have achieved biexton binding energy of 60.3 milli-electron volt. And also biexton binding energy, biexton peak is located at the lower energy side compared to the exton peak. So this means that biexton binding energy is positive. Okay, so this is the plotted summary of the many reports, other groups' reports on biexciton binding energy versus exciton emission energies. This is our report here, and also this is another report in our group, and both are larger. The absolute value of the both biexciton binding energy is larger than 23 billion electron volt. Particularly, nanowire quantum dot laser, gallium nitride nanowire quantum dot shows 60 million. This can be also partly explained by the calculation. We did collaboration with Technical University of Berlin. And here we find that the aspect ratio is the most important, one of the important parameters, and the larger positive binding energy is attributed to small aspect ratio of the quantum structure. So then we try to measure the autocorrelation effect at the various temperatures from the quantum dot structure, nanowire quantum dot structures. And here at 4 Kelvin, of course, we have the single photon emission. At 150 Kelvin, we see single photon emission because anti-bonding is clearly observed. So we tried room temperature operation, and we have nice anti-bonding effect even at room temperature. The energy broadening is 36 millielectron volt. This is much smaller than the biexciton binding energy. So therefore we can see such kind of anti-bonding effect. So even we also elevated temperature up to 350 Kelvin that we see anti-bonding effect even at this very high temperature. This is the temperatures at which you can have the void X. So, okay, so this is some kind of summary of operation temperatures versus wavelengths with respect to many kind of gallium single photon emitters materials. So concerning operation temperatures, wide gap, band gap material is much better. This is our point here. And with the increase of the band gap, or with the increase of the wavelength, with decrease of the band gap, operation temperature can be reduced. This is the G20 values. And concerning the quality of the single photon, still the single photon emitted from near 1 micron is the best. So we need to challenge more and more in order to realize high temperature operation and high quality single photon generation. Okay, finally, I just mentioned the applications, and quantum lasers for telecom is of course my main feature. And also recently we are working on intensively the laser manufacturing is based on the high power operation, and we find that this high power operation can be realized or suitable, even suitable for compared to quantum wave high power laser. And of course, optical interconnect is very important for 5G connections or the high performance computer systems. And quantum communication and computing and quantum dot will play very important roles. And also, I want to mention that quantum dot solar cell is a very important application in the future. Theoretically, we can achieve the conversion efficiency of the over 75% using multi-level quantum dot solar cell structures. And but still, it is not so easy because we have to completely homogeneous quantum dot structure. And quantum dot can be applied to also photodetector and sensors using inter-subband transition. We are working on the emission and so on for this application. In addition to this, quantum dot displays and quantum dot biomarkers are very important, particularly for carbon neutral issue. Quantum dot display is very important for low power consumption displays. Of course, these two applications at the present stage, colloidal quantum dots are utilized. Okay, so this is the statistics of the quantum dot. The number of quantum dots, number of papers published with the keyword of the quantum dot. You see that the number of papers is still increasing regarding the quantum dot research. Okay, finally, to summarize, in my talk, I discussed the progress in semiconductor quantum dot, and that has been reviewed with emphasis on light sources. And the quantum dot lasers are now commercially available, and the most promising light sources for silicon photonics. And the quantum dot single photon sources are also promising single photon, English is not so good, and particularly at the telecom wavelengths. And quantum dots also provide a platform for a variety of semiconductor quantum computing systems through their qubit functionalities. Mainly, this is at present electrical. Finally, quantum dot displays and other quantum dot devices will be one of the most important devices for realizing a carbon neutral society. Okay, so thank you very much for your great attention.
Well, thank you very much, Professor Arakawa, for giving that exciting talk, starting from the fundamentals and the discovery and the theoretical development from you, and then to the wider, broad range of applications. It's really been a fascinating talk. And I'm sure that all the audience have enjoyed this one very much. So now let me go to questions, and so see some of the people, those are asking questions, and then we've received many questions, but what we do in this case is that we try to restrict ourselves to 3 questions because of the time limitations. So the first question is YC Lee from Shenzhen, and thanks, Professor Arakawa, for sharing your invention of quantum dot laser, and it took about 20 years from academic innovation to a real product. Can you tell us something about the collaboration with the industry? What is the biggest issue you met at this time period?
Of course, yeah, I proposed the concept of quantum dot in 1982, and this was, and also on the other hand, the venture company was started in 2006, and quantum dot lasers were commercialized in 2010. After 2010. So therefore, as mentioned in this question, it took more than 20 years. Probably this is one reason is that it took time to realize quantum dot structures, high quality quantum dot structures for a long time, and actually. So therefore, this is one of the technological issues, and which causes such a long time delays to commercialization from the first proposal. But so therefore, I can say that one main reason is we need technological progress, and the second reason is that it was not so easy to convince company people that quantum dot laser is really useful. So therefore, before demonstrating the high temperature stability of the threshold current in quantum dot lasers 2006, the company were not seriously working on that, except Fujitsu and so on. So after we showed nice demonstrations with high temperature stability, people noticed that the importance of the quantum dot lasers. And also, now many people in the world convince themselves that for silicon photonics light sources at 1.3 micron, quantum dot laser is the best light source. This was also convinced by our effort. So therefore, it is very important to demonstrate high performance effect, high performance characteristics by ourselves to make sure to convince the industry people that it is very important.
Okay, very much. Yeah. It's a long journey, but I think you have succeeded in achieving that goal. Thank you. The next question is from Max at ETH, and a wonderful talk. Thanks, Professor Arakawa. As you mentioned, material is the key. Could you give your perspective in this direction?
Okay, so I'm thinking this question is related to quantum dot lasers on the single photon sources and so on. And so therefore, if I suppose that this question is related to quantum dot laser, we need to develop high quality quantum dot suitable for 1.5 micron wavelengths. Already, there are several groups which demonstrated nice performance of the quantum dot laser at 1.5 micron, but still we need to make effort to improve the material issues, including lifetime and so on. And but by making within 10 years, we can solve the problems, and we believe we can realize the commercialization of the quantum dot laser at 1.5 micron with high performance, such as high temperature operation and so on, and high temperature stability. And concerning single photon sources, still we need to investigate material issues. We don't know what will happen in the future, and so all, including you, should work on developing high quality material that realize, for example, high temperature operations and also high quality single photon generation simultaneously at the same time.
Okay, thank you very much, Professor Arakawa. So the last question is from Xinqiang Wang from University of Tokyo. Perovskite quantum dots are emerging materials. What is your opinion on their future in science and industry?
Yes, perovskite material is very important, and also several groups investigate perovskite quantum dot structures. Probably this is for solar cells and also other applications. Regarding the application to science such as quantum dot telecom lasers or single photon sources at telecom wavelengths, probably this perovskite quantum dot cannot be utilized. I think for solar cells materials, perovskite quantum dot are one of the very promising structures which are suitable to be investigated. I'm not sure this can be successful in the future. This will be successful or not. And still, we need to continue the basic research.
Okay, thank you very much, Professor Arakawa. Thank you for this wonderful lecture as well as answering all the nice questions. So now let me move towards the panel discussion. And in addition to Professor Arakawa, then we've got our challenger and Changhao Li. And Changhao Li is from MIT, and he's a PhD student there. And then before moving to MIT in 2017, he has done his bachelor's degree in physics from Xinqiang University. And then he's really doing beautiful work at MIT. He's a rising star and publishing papers in physical letters and nano letters and the Nature Journal of the Quantum Information. So really, it's great to have the Changhao Li. And also, we've got a very distinguished colleague here as a guest and a panelist, and this is Professor Xinqiang Wang from Peking University. Professor Wang is, of course, knows Professor Arakawa very well, and he collaborates with him. And he has also done major work in the area of semiconductors and working on nitride semiconductors and quantum dots and nanowires and zinc oxide and a wide variety of materials. So let us welcome Professor Xinqiang Wang, our panelist. And Professor Wang, you may like to unmute yourself, please. And great to have you here. Thank you for joining us. And also that Mr. Changhao Li, please unmute yourself also, Mr. Li, and welcome to the panel discussion as well. So generally in this discussion, of course, we've got our host here, and then Professor Alice Zhang, and then Peking University, and then she is the person who really initiated these iCANX talks and then really makes things happening. You know, we're all there at the front, but she is the person who really, you know, everything is happening because of Professor Alice Zhang. Thank you very much, Alice, for your wonderful efforts really promoting science and scientists. We're delighted.
Thank you, Professor Jagdish.
Okay, now let's go with the panel discussion, but maybe we'll generally give the opportunity for the challenger to ask the first question and then see if he has got any specific question. Which Mr. Li, would you like to have any question which you would like to ask Professor Arakawa?
Yeah, sure. Thank you very much for the introduction, and thanks Arakawa Sensei for this really wonderful talk. I really enjoy it. So in your talk, you mentioned many advantages of the quantum dot laser, such as high temperature operation range and high temperature stability. And also there are already many commercial applications of quantum dot lasers. So what do you think about its future direction? And more specifically, could you talk about what are the current challenges or disadvantages for the quantum dot systems for their application in laser systems?
Yeah, so as I mentioned in the last slide, there are lots of applications of the quantum dot laser in the future. Particularly, I'm very much the following is the most important: optical interconnect application. So this will be our silicon photonics application. This will be indeed very important because already the electronic interconnect will be matured and between the chip to chip, and but we need more transmission between the chips of the information. So in order to overcome this issue, optical interconnect must be playing very important roles. For this, we need light sources near the LSI chips, and but we cannot avoid the heating effect. From this point of view, with this quantum dot laser will be almost unique solutions for the light sources for optical interconnect. So therefore, I said that the first important market or the application is optical interconnect or silicon photonics. Also, the secondary, so now, laser manufacturing technology is very important. And for this, we need high power lasers. Currently, fiber laser is the most popular one. And however, efficiency is 20% or something like that. In order to overcome the limit of the efficiency, so many people are now trying to use the semiconductor lasers directly for the laser manufacturing. But if we use the quantum lasers, the efficiency can be up to 60%. However, if we use quantum dot lasers, efficiency can be up to 80%, because even if junction temperature is increased with a high injection current, the threshold current does not change. So therefore, we can keep the linearity of the IL characteristics with a more higher power output. So therefore, we can keep the high efficiency of the light sources for laser manufacturing. This is the second application. And the third is, of course, quantum dot lasers and also quantum dot light sources will be utilized in many kinds of quantum communications and also quantum sensing, or even quantum computing. And still, quantum computer system is a dream. However, in the future, we have to connect the cryo environment and also the room temperature environment. For this, optical interconnect will be very useful. For this purpose, also quantum dot lasers or quantum light sources will play a very important role. Also, needless to say, quantum crystal communication. Ultimately, we should use single photon sources, and for this purpose, quantum dot single photon sources will be playing very important role. Okay, this is.
Thank you. Yeah, that's very good answers. Yeah, thank you.
Okay. Thank you very much, Professor Arakawa, and thank you, Mr. Lee. And maybe we'll ask our guest panelist, Professor Wang. And Professor Wang, would you like to ask any question or want to really discuss anything which is specifically which you want to ask?
Let me ask two questions from Professor Arakawa. First question is, how long do you expect when we will win the Nobel Prize? I think that the quantum dot is when possible, not long time, right? Probably.
Yeah, it's up to you.
So we are expecting. So the second question is, for example, you just give very nice report on the 3.5 quantum dot laser, basically arsenide. And how do you think on the nitride? What is the difficulty if you want to realize nitride-based quantum dot laser?
Yeah. So one of our dream is to realize nitride-based quantum dot lasers, and we have been working on realization of the gallium nitride-based quantum dot lasers for a long time. And the advantage of the use of the quantum dot in the nitride semiconductor is much enhanced compared to the use of quantum dot lasers with arsenide material, gallium arsenide material systems, because the effective mass is much larger in the wide bandgap materials.
Yeah.
Of course, I cannot explain the details, but here I want to stress that it is very advantageous for nitride quantum dot to realize quantum dot structures or the lasers. So therefore, I have been making effort. But as you know,
Yes.
it is not so easy to realize high quality quantum dot structures with gallium nitride-based materials. So therefore, you and also other colleagues in the world will continue to make effort to realize gallium nitride-based quantum dot lasers. And finally, I hope someone will demonstrate high-performance gallium nitride quantum dot lasers. Maybe student and so on.
Thank you.
Okay.
Okay.
Professor Jagdish, can I ask a question?
Please go ahead, Alice.
Professor Arakawa, there were one question is coming later from audience. Is from MIT, Xinqiang Wang is asking for the quantum dot laser. Can that possible used to build up integrated chips, photonics chips, to be used for quantum computing? And what's your opinion on this?
Yeah, I think so. And quantum dot can be utilized for both electronic qubit and also optical qubit. And also, this can be applied to optical quantum interconnections and so on. So therefore, quantum dot should play a very important role for future quantum computing systems. And of course, for electronic qubit, maybe at present stage, quantum dot formed by the electric potential control or electric field or depletion field effect will be more promising at the present stage, because they don't need to use electron hole pairs. They need to just use electrons. So therefore, they can utilize depletion effect for the confinement of electrons three-dimensionally. Indeed, there are several groups in the world that that are working on the quantum qubit using quantum dot formed by the depletion effect. But for optical quantum qubit, we definitely need electron hole pairs. In this case, we need to have real three-dimensional confinement structures, and this should be investigated more intensively for future quantum computing systems, including optical quantum computing systems.
Okay, thank you very much. Yeah. Maybe I ask one more questions. Okay.
Yeah, sure. Please go ahead, Alice.
Just to follow, Professor Wang. Yeah, his question is about the Nobel Prize. Actually, this was a topic in China. Almost many Chinese people was talking about this. Why Japan, wins so many Nobel Prize? Yeah, especially, recently, almost 1 year once in science. So in China, we are really looking forward, how to learn something from Japan. Yeah, I saw you did, all this innovation when you are very young. Then you focus on these topics for many years. So can you tell us some secret for the system and how the, education system training you?
Yeah, of course, this is a very interesting discussion. But I guess in 30 years, there will be many Nobel laureates from China, I guess. And yeah, so you can. So I believe young students and also young researchers in China will be producing the more innovations, and also the population of China is 10 times larger than that of Japan. So therefore, suppose that there is one smart student in Japan, 10 students in China will work on that. And the most important is for young people to continue to work without being disturbed by the funding. And so, I mean, you should consistently work on one thing, and you should focus on the direction which you believe.
Okay.
If, in order to get the Nobel Prize, you have to do have the research which has not been done by other people. So therefore, you should not challenge the popular subject at the present stage. You have to find out by yourself a new subject. It's very tough work. You have to be patient, but it is important. But this is a necessary condition, but not sufficient condition. So even if you continue to work unpopular subject, you cannot get the position. I mean, it depends on your philosophy and also your direction. But I hope that you find new good subject you good problem by yourself. Then the result will be might be led to the innovation or Nobel Prize.
Well, thank you very much. That's a very important answer. The people should to find out, the questions no one answered, right? The directions, no one touched. And then one, dimensional. You're just working in this way. Okay. So,
I guess,
Professor Jack.
Just one more. I think
Go ahead, Professor Wang. Go ahead.
I mean, for China, it's time. I mean, Professor Arakawa is right. Maybe in China, some research status is much better compared to 30 years ago. And after 30 years, I think there will be many researchers are able to win the Nobel Prize, because now, particular like Professor Arakawa said, young students have the chance, and we have already everything ready for them to study one thing concentratedly, somehow with like a hobby. That would be great. Thank you.
I agree with Professor Arakawa and Professor Wang, and I think China has got a bright future. And then I guess has been mentioned that the Chinese government has been investing quite heavily in science and technology during the last 30 years or so. There are lots of bright young people out there. It's only a matter of time. Nobel Prizes will follow. That's why the important thing is that governments should continue to invest in science and technology.
Yes.
I think what amazes me is that Professor Arakawa is able to get the funding for quantum dot work 40 plus years. So that probably the message is that funding agencies should not lose patience and continue to fund the research which is important. I think Professor Arakawa has been very successful from that point of view. Would you like to comment on that one, Professor Arakawa, how you have been successfully able to convince to fund your research for 40 plus years?
But please note that when I started to work on quantum dot, or when I proposed the quantum dot in 1982, I was so young. So therefore, my funding is very small. And we have just, the university gave me some constant money. And based on this money, I worked on that. So therefore, even if you are very poor professor, you can have a chance to create a new thing by concentrating yourself on the thinking. But after that, once we have some kind of new idea, then it is very important to accelerate the research by getting more funding, bigger funding, and so on. So for this, we need to convince the government people or the funding people to so for example, my research is very important for the future of the engineering, the physics, and so on. Thank you
thank you very much.
Thank you all of you for your very good questions.
Thank you. Maybe we'll give the last opportunity to Mr. Lee, our challenger, to ask the last question before we close the session. Mr. Lee, do you have any further questions to Professor Arakawa?
Yeah, thank you very much. Thank you for giving me this opportunity to ask the last question. So Arakawa sensei, you just mentioned about the young scientists. So my last question is about do you have any general or specific suggestion to young scientists who just, for example, just finished their PhD or just finished their postdoctor and they just begin their career in science? Do you have any suggestions to them, and any lessons and experiments you might want to share?
So if you just finished the PhD or the postdoc and so on, of course, you can continue to do the same research, and or you can switch your field to a new thing. And so it's up to you. And so sometimes it is more efficient to continue to the same research, but sometimes to get create a new innovation, you can challenge a new subject. In my case, until 1980s, I was working on optical communications, and of course with optical communication theories. But I switched my field to optical devices, and at that time, I searched very carefully, or I thought very carefully what I should do, and I tried to find other big group, try to find new subject which have not to be done by big group. That's the reason why I selected the quantum effect in lasers. This is of course, this was inspired by Lewis and so on, but so therefore, when you finish one thing, you can think for a moment what you should go, and you can challenge completely new things, and also you can continue to deepen what you have been doing. And so anyway, I hope you are good luck. Thank you.
Thank you for the answer. Yeah, that's very helpful.
Okay, thank you very much, Professor Arakawa, and also thank you, Professor Wang and Mr. Lee, and of course, Professor Ali-san. And Professor Arakawa, before you leave, and we, on behalf of the iCANX organizers, and we would like to present to you this certificate. And of course, if you had met in person, we would have given you this certificate. And but we'll send you through mail, and Alice will. You will get the certificate.
We hope to hear the best news in October. I think maybe,
October, November, it's right.
Yeah, let's hope so. Let's hope so. So also,
thank you very much.
Thank you very much, Professor Arakawa. Again, we are grateful for that one. For just announcement, next week, Professor Naomi Hallis from Rice University is going to talk about nanomaterials and light applications, and Professor Paul Weiss is going to moderate the next week's session. And then also we've got Challenger from Cornell University, and also panelists from South China University of Technology. And then it's going to be an exciting development talk, and then hope most of you will come back and join us again. Thank you very much for joining us for iCANX Talks. And again, every Friday at 8 p.m. And if you want to learn about science, and iCANX Talks are the ones to really spend your time. Thank you very much once again to Professor Arakawa and Professor Wang and Mr. Lee and Professor Ali-san for making this happening. Thank you very much, and have a good evening.
Thank you very much.
Yeah.